And welcome everybody this morning to the second day of lectures in this Quantum Dot School. Let me share my screen with you. I hope you can see the screen I just shared. And as Professor Manna already mentioned, let's kick off this day with a discussion on how to make two-dimensional cadmium selenide-based colloidal nanocrystals and how we can understand a little bit their optoelectronic properties once we prepared a series of these samples with various sizes and thicknesses. So probably you already heard yesterday, the Quantum Dot School deals with colloidal quantum dots, colloidal nanocrystals, which are typically these small spherical crystallites, which can be made between roughly 2 and 20 nanometers. And because when they are semiconductors, they are very small, you can actually tune the optical properties, not by varying the composition of the material anymore, but by simply changing the size of the crystallite. Here I give you an example of a typical series of cadmium selenide-based nanocrystals, where the large ones here on the right emit in the red part of the spectrum. And as you decrease the size, you can see you can make them emit all the way into the blue and even UV region. So why is this happening? This is, of course, because when they are so small, their optical properties are dominated by quantum mechanics. The particles inside that you excite with light, for instance, the electrons and holes that you create in this way, don't behave simply as point particles anymore. They actually behave as waves. And in order to make this a little bit understandable, I would like to start the lecture of today with a short summary of what happens in a bulk semiconductor. And even when starting from free space, when you do the calculation of the behavior of a free electron in free space, you see that you actually have not a point particle as mentioned, but an electron represented as a wave packet, which moves through free space with a certain velocity, which also gives it then a linear momentum by multiplying the velocity with the mass of the electron. Now, when you move from free space to a semiconductor bulk crystal, the behavior of electrons moving through that crystal can be described in a fairly similar fashion. However, the periodic crystal itself, and more specifically the, say, colloidal interactions of the electron with the periodic atoms here depicted in a linear chain, make it change its behavior a little bit in a way that we can say that it moves like a nearly free electron. However, there are certain energies, there are certain momenta here which are restricted because there are certain energies for which the particle can no longer move through the crystal, and it actually forms standing waves. Yeah. So when you have a standing wave, this means that for this momentum, for this energy, the movement is not allowed anymore, which means that there are inside your band structure certain regions here for which the energy, for which the electron can no longer propagate. And this region of space for which propagation is forbidden, we call the band gap of the material. Yeah. Now, going from a bulk semiconductor to a two-dimensional quantum well, if you want to understand the behavior of electrons moving through a quantum well, in fact, it can be described in a very similar fashion as for bulk semiconductors when you go through X and Y movements. However, in the Z direction, due to the finite thickness of the quantum well, of course, propagation is again restricted. Now, how do we do this? So how do we approach this mathematically? Well, mathematically, we can say that we can solve the Schrödinger equation for the behavior of this electron wave function in 3 dimensions in this way. However, we can separate this 3-dimensional wave function into behavior along the z direction, the confined direction, and behavior along the xy direction. If you decouple that, I just want to emphasize here now that this here is its behavior along the z direction, where due to the restricted motion, you have these so-called standing waves. So this is just the same as for bulk semiconductors. This, however, is modified when you go from bulk to quantum well. And I would just like to zoom in a little bit more on this equation here. If you would solve it by a particle in a box approximation, you see that this Schrödinger equation reduces to this one here. And by the way, just as a general comment, I give you these equations. However, it's not the idea that we make a full derivation of these equations today. Most importantly, I want you to say, grasp the notion that for instance, in this case, the Schrödinger equation can be solved here in a particle in a box well approximation, and that we have certain solutions for that. Okay, so just to go back, the Schrödinger equation for a particle in a box in 1 dimension looks like that. It has a potential equal to 0 inside the box, and it's infinite outside the box, which means you can only have solutions in the form of standing waves here, which are a combination of a cosine and a sine function. Yeah, if you solve this completely, you'd see that the standing wave solutions are actually given by this sine wave solution here, with k equal to this number here. So the first one has a solution k equal to pi over L, then we have 2 pi over L, then we have 3 pi over L, and so on. Yeah. Now, very importantly, you see that k depends inversely proportional on the width of the quantum well. So this means you already can see a first effect of quantum confinement. If you make the quantum well smaller, the energy levels go up, the k numbers here go up. The energy levels themselves are actually here given by this solution here, and read that the energy of the standing wave solution corresponds to h bar squared k squared over 2 times the mass of the electron in this case. Okay, so in Z we have only discrete solutions to our Schrödinger equation. This means that if you plot this so-called dispersion relation, which is a parabolic equation, you see that this gray line represents the general solution, but for the quantum wells, we only have here solutions at discrete k values. We have energies occurring at discrete energy values. Okay, and as I said, most importantly, the energy depends on k squared, and k being inversely proportional to the width of the quantum well. This means that here in this case, you see confinement acting. By reducing the quantum well, you increase the energy of the individual wave electron states. Okay. So in a nutshell, we can solve the Schrödinger equation for a particle in a box when we go from bulk to quantum wells, and understand how the band gap, how the energy levels of such a material vary. I give you this general slide here today as well, because not just 2D quantum wells can be synthesized as colloidal nanocrystals. You also can make here nanorods, nanowires. You can go even into quantum dots. However, for the lecture of today, we will mostly, and in fact solely focus on colloidal quantum wells, which we also call colloidal nanoplatelets. So why are these colloidal nanoplatelets then so interesting? That's because we can say have a very good control over the optical properties through the colloidal synthesis. I show you here this example of 3 nanoplatelets with different thickness. You can see you can have a very nice sharp absorption spectra, which then shift here in discrete steps as you increase the number of layers for this colloidal quantum well, for this nanoplatelet in the thickness direction. But since we're working with colloidal chemistry, in addition, we can also tune here the lateral dimensions, the X and Y dimensions of this nanoplatelet, and have an additional modification or tuning of the band gap of such a material. Furthermore, in comparison with colloidal quantum dots, we see that because these are extended platelets, they have a very flat shape, they actually have faster emission rates than colloidal quantum dots, which may be beneficial for certain applications. I am thinking, for instance, of the quantum communication, say, technology, where you really want to have photons coming out of your material at a very fast rate. On the other hand, the same effect, the fact that you have this two-dimensional shape, makes sure that you have a very strong absorption coefficient. And finally, these platelets can actually be synthesized in solution having all exactly the same thickness. And this is an important difference between these nanoplatelets and colloidal quantum dots. And because they all have the same thickness, their absorption and fluorescence spectra actually become more narrow than what you would have with colloidal quantum dots, because the latter ones are always broadened a little bit by heterogeneous size broadening, which we don't have in these platelets. So they're very interesting materials to synthesize, to have a look at optoelectronically, to think of applications for. And I would just like to briefly discuss the synthesis with you so that you understand how we can make them. Because essentially, the colloidal nanoplatelet synthesis is not that different from the synthesis of a quantum dot. We actually indeed start with a normal quantum dot synthesis to produce very small seeds or clusters of cadmium selenide. But then what's different is that we inject here a short-chained molecule in the form of cadmium acetate. So compared to the typical organic ligands that you use during quantum dot synthesis, which are oleic acid, or in this case, myristic acid, which are long organic chains, we add here this cadmium acetate. The acetate has a very, say, short chain. It modifies the solubility of your precursors and drives the synthesis in what we call a so-called kinetic regime. This kinetic regime means that there is a very high supply of precursors to your material, so it can grow very quickly. And in that case, the growth is actually dominated by the difference in nucleation thresholds for nucleation and growth on a wide facet and nucleation and growth on a narrow facet. And the group of Norris a few years ago actually very nicely demonstrated that the nucleation threshold to nucleate material on the narrow facets and then have the narrow facet grow into a complete layer is much smaller than the nucleation threshold for nucleation on a wide facet. This practically means that this facet grows orders of magnitude faster than growth in the Z direction. And you spontaneously get these anisotropic nanoplatelets. By doing this and tweaking the synthesis a little bit, you see you can make now nanoplatelets with a thickness varying between 3 to 5 cadmium selenide monolayers. Now, this also poses a problem because if you want to study the optoelectronic properties of these materials, you do want to have access to a little bit more than just 3 thicknesses. But you also can appreciate from this reading a paper that the reaction mechanism intrinsically limits the thicknesses that you can obtain by this synthesis. Why is that? That's because at some point when this narrow facet becomes thicker, the nucleation barriers will become more and more similar, up to a point where thicknesses beyond 5 monolayers are really difficult to produce by this synthesis. However, we found a solution to that, and it was a solution in the form of modifying this 2-dimensional growth back into a 3-dimensional growth. And from previous work, we knew that, for instance, cadmium chloride was very efficient at inducing a very fast growth of colloidal nanocrystals in all 3 dimensions. Now we applied this also to this synthesis. So what we did is we first synthesized here a normal 4.5 monolayer cadmium selenide nanoplatelet, but then we added cadmium chloride to this reaction mixture. And you can see what happens then. In fact, instead of just being limited to 3 to 5 monolayers, we have the growth of very thick platelets, which in this case have an absorption around 580 nanometers. By studying the amount of material that grows as a function of time, we also noticed that this was actually a synthesis where the nanoparticles grew through Oswald ripening. And what we believe and is happening, and which was also confirmed by beautiful work here done in the Talapin group, is that indeed here you can switch from 2D to back to 3D growth by changing the nucleation barriers here for the nano and the white facets. So we think that the cadmium chloride is actually absorbing on these edges, on these facets, hereby reducing the nucleation threshold for the white facets and making it more similar to the one of the narrow facet, enhancing the 3D growth again. So this shows you that at this point, we can now make not just 3, 4, and 5 monolayer platelets, but even go to 6, 7, and 8 monolayer nanoplatelets with emission extending all the way into the red. We still had a problem with the blue nanoplatelets because we could synthesize them, but if you follow this procedure developed by Sandrine Inturia in the Dubertrek group, you would notice that when you want to modify the synthesis of cadmium selenide platelets to the blue ones, typically what people do is they simply reduce the synthesis temperature. Now this works. The seeds that you produce are smaller, but also the number of seeds, the nucleation rate goes down. And what happens then, there's a lot of material left to grow the nanoplatelets, and they grow into very big sheets. Now, from an optoelectronic point of view, this is not so convenient because these sheets, they have very strong trap emission. These sheets also have a low fluorescence efficiency, so you can't do much optoelectronic studies on them afterward. So we tried to solve this problem by adapting the synthesis a little bit, which worked actually very recently. And the way we modified it was actually just simply increasing the selenium concentration to push this nucleation rate up a bit. But then in addition, we also had a look at the effect of the long-chained ligands attached to the cadmium precursor. So typically you would do the synthesis with cadmium myristate, but instead of just using cadmium myristate, we went from cadmium octanoate to here cadmium stearate, which is a C18 chain length. What is nice is that we can already see that the synthesis is producing smaller nanoplatelets because we have a very gradual shift of the absorption spectrum as the synthesis progresses. And this means that indeed we are changing confinement in the lateral dimensions. So we're changing the width of the platelets. But what was more interesting is that when we had a look at how these ligands here also affect the synthesis, because you have to remember that these platelets, they're always covered in ligands, even during synthesis. We see that when you go from cadmium octanoate, where you produce fairly large sheets still, all the way to cadmium stearate, you start to produce the very thin nanoplatelets here. And what we think is happening here is that when you start to use these very long chain lengths, they actually pack into a very nice self-assembled monolayer along these edges. So by packing into a very compact layer along the edges, you actually can reduce the growth along this direction as well. The good thing is that we now have platelets with very good fluorescence properties, which makes them suitable for further optoelectronic investigations. So a first example I want to give to you today is how you can understand the nanocrystal thickness, the nanocrystal band gap. We did this by taking all the samples that we had, measured the experimental thickness with a TEM, and then comparing to the band gap that you obtain. Now, you can fit this, these results into a so-called sizing curve, or which represents the evolution of the band gap as a function of size. This is more or less the bulk band gap. It's slightly smaller, but it's more or less the bulk band gap of cadmium selenide. But more importantly, what we noticed is that here the band gap changes with 1 over d, 1 over the thickness of the nanoplate. So this was already quite, say, surprising to us. We also checked then, in addition, how the band gap changes as a function of the width of the nanoplatelets. And there, in fact, the width follows a nice 1 over w squared dependence. We checked this for 3.5 monolayers. We checked this for 4.5 monolayers. In these cases, we both found the same dependency on the width of the nanoplatelet. So as the width becomes smaller, the band gap goes up, and it goes up with 1 over w squared. So combining everything together, you see you can get this general sizing curve. But again, I want to emphasize that although the width goes with 1 over w squared, the thickness goes with 1 over d only. So how can we understand this behavior now, based on what I said earlier, that if you want to model a quantum well, that the energy level of the band gap goes with 1 over the width of the quantum well squared? Well, one first important approximation that we made was that if we solved the first example of the quantum well in the beginning of the lecture, we actually assumed that the potential outside the quantum well is infinite. But this is actually an approximation which is not strictly valid, because you have the quantum well here, but the surroundings are essentially dominated by the ligands, the organic solvent, and although the band gap of this material is very large, it's still finite. Yeah. So the potential well is not an infinite potential well, it's a finite potential well. And this means that the solution to the Schrödinger equation shows that you have some leakage of the electron hole wave functions, of the exciton wave functions into the surroundings. Now, when you solve the equation here with a finite potential well, you see this leakage. You can also appreciate that if you now start to make thinner nanoplatelets, this leakage will become stronger and stronger. And this means that what you would expect from an infinite potential well is no longer valid. And the confinement effect is slightly reduced by the fact that this electron wave function will start to leak more and more into the surroundings, decreasing the quantum confinement effect a little bit and weakening the size dependence of the energy on the thickness of the nanoplatelet. So this is in the first effect, which is modifying here the band gap of the material. And in the very strong confinement regime in which we are working, because these platelets are only, say, 1 to 3 nanometer thick, you have this leakage and a reduction of, say, the square dependence of the band gap of the thickness. A second effect that I also would like to discuss with you, because this also applies in general to quantum confined systems, is the concept that we could model the electron behavior by a momentum which was given by the velocity and the mass of the electron. Now, again, I don't want to run into the full derivation of the velocity of and mass of this system, of the system of semiconductors. I just want to emphasize that the mass of an electron is actually related to the curvature of the conduction band. The mass of the holes is related to the curvature of the valence band. Mathematically, it's given by this expression here. So the mass of an electron in a semiconductor, the effective mass of that electron, is given by h bar squared divided by the second derivative of the band, the conduction band, to the momentum. And what we have in bulk semiconductors then is that typically this is expressed by this, quadratic dependence, which gives you a constant second derivative and a constant effective mass. But like I said, now focus on this mass a little bit and understand that when you increase confinement, the first energy level that you can encounter occurs at finite K values, and this can depart from the bottom of the conduction band quite strongly. It can depart from the bottom of the conduction band so strongly, actually, that this parabolic approximation that we make for the bottom of the conduction band, which gives you this constant electron mass through this equation here, this approximation is actually no longer valid. And you see that the actual dispersion curve here is no longer parabolic. But if it's no longer parabolic, this means that the effective mass can change. So for colloidal nanoplatelets, which are so strongly confined because their thickness is so thin, the first energy level that you encounter comes at a K value, which is so far away from the center here, that the approximation of having a constant effective mass for the electron, which is equal to bulk, is no longer valid. So I want to emphasize that we didn't do here a full mathematical derivation of what the actual effective mass is, but because of the fact that you can have some variation here. It also means that in case when you have this kind of deviation, where it increases less than the parabolic behavior, you would see actually an increase of the effective mass. And since an increase of the effective mass lowers the energy level, you would see that it effectively depends on the thickness by a scaling factor which is less than d squared again. Okay? So I would say from this first part of the lecture, I think the most important thing I would like you to remember is that confined systems in first approximation can be understood by solving the Schrödinger equation for these systems, that from an infinite potential well, you would expect a 1 over d square variation of the band gap because of confinement. However, due to the fact that we work with finite potential wells and due to the fact that the effective mass of the electron can change, practically for cadmium selenide, we see that it only varies with 1 over d. In the XY directions, we did recover the 1 over W, with W the width dependence, but this is probably because in the width dimension, we don't reach this very high confinement regime. The width of a nanoplatelet is typically varying between 3 and 20 to 50 to 100 nanometers, but because of the fact that they don't go into this 1 nanometer regime, we do recover the expected behavior of the band gap variation with 1 over W squared. Okay, so this is already nice. At this point, we can understand how quantum confinement acts on the band gap of a confined system. So then for the second part of this talk, I would like to have another look at the actual absorption behavior in colloidal nanocrystals in colloidal nanoplatelets. And to understand absorption, we again have to here remember or acknowledge the fact that these quantum dots are typically produced in solution. So this means that the optical constants, the dielectric constant of a quantum dot, when it is suspended in an organic medium, differs very much from this organic medium. Typically, values for the dielectric constants of semiconductors, 10 and 25. Typically, the dielectric constant for organic solvents is around 2. Now, due to this difference, when you apply an electric field, or in other words, when you shine light on, say, a semiconductor nanoparticle in suspension, the field inside the quantum dot will not be the same as the one outside. Because what happens is that due to the, say, finite size of the nanoplatelet, of the nanocrystal, when you apply an electric field, you will have a so-called polarization of your medium. So the electric field will shift the electrons up a little bit, causing a slight negative charge on the top of your crystal, a slight positive charge here on the bottom. And due to the fact that they are embedded in a medium, an organic solvent with a different dielectric constant, on the outside you have the opposite effect. So there's a slight buildup of charges, negative charges on the bottom, slight buildup of charges here, positive charges on the top. This causes this polarization of the nanocrystal, and since the polarization has an opposite direction as the initial electric field, the field inside the nanocrystal is in fact slightly reduced. If you want to understand this intuitively, one could say that when you shine light on a nanocrystal, the actual light going inside the nanocrystal, the amount of light that can be actually absorbed is less than what you have outside shining in on the particle. Yeah? The difference between the electric field inside and outside we call the local field factor, which is the ratio of E local divided by E naught, and it's actually simply related to the optical constants of your material. Again, if you want to understand more, I strongly encourage you to read this paper here by Sivula, which very nicely derives this equation here. Suffice it to say that the local field here depends on the dielectric constant of the solvent divided by the dielectric constant of the quantum dot plus 2 times the dielectric constant of the solvent. Yeah. Now that this modification is very strong, you can also appreciate by the calculation of the absorption coefficient of materials, of semiconductors. I show you this example here, where in blue, I plot the bulk absorption coefficient of lead sulfide. And then in red, I plot the theoretical absorption coefficient of a lead sulfide nanoparticle. And you can see that the absorption is strongly modified. Now, I want to emphasize this has nothing to do with confinement, with quantum confinement now here. This has only to do with the fact that there is less light going inside the nanoparticle as you shine in on it, just because the optical constants, the dielectric constant of the quantum dot is different from the environment. And the modification can be very strong. Yeah? Now, a second step I want to take in this discussion is then the notion that this is a shape-dependent effect, because it's essentially electrostatics. It's an electrostatic calculation of the polarization of such a nanocrystal, but the polarization is depending on the shape of the particle. Only when you have a sphere, you arrive to the equation I just showed you before. When you have, for instance, a nanorod, you see that the absorption properties become anisotropic. And in fact, the absorption coefficient of a nanorod, when you shine light with a field polarization which is parallel to the long axis, is strongly enhanced, especially for high aspect ratio particles. On the contrary, when you have here the electric field shining in with a polarization parallel to the short axis, the absorption coefficient is slightly reduced. Now, again, intuitively, you can appreciate this from the notion that this polarization, due to the fact that you have a long rod now, pushes the charges, the excess charges, further away from each other. And it's more difficult to polarize a rod along this direction compared to a sphere. Now, since it's more difficult to polarize it, there's more light going inside your nanorod when the polarization is parallel to the long axis. When there's more light going into your nanoparticle, you will have a larger absorption. Now, if you work with, say, nanorods in practical settings, in dispersions, of course, you have to average this behavior out over all possible orientations of your nanorod in solution. Even if you do this averaging, you would see that on average, the absorption coefficient goes up with aspect ratio. So a sphere absorbs less than a long nanorod. And for a nanodisk or a nanoplatelet, this effect is even enhanced further. You can see that compared to a sphere, there's about, for cadmium selenide, 1.5, 1.6, 1.7 enhancement of the absorption if you go to long rods. If you go to very extended nanoplatelets, you can get an enhancement of the local field, of the field inside your particle, by a factor of 2.5. And this is one of the reasons why nanoplatelets have stronger absorption coefficients compared to quantum dots. But it also has a very strong influence on the fluorescence of the nanoparticle. And this I show you in this equation here, which is the so-called Fermi's golden rule. Because Fermi's golden rule here states that the absorption strength, and therefore also the emission strength or the emission rate, depends on the intrinsic oscillator strength of the transition. In other words, the, say, electron-hole overlap. It also depends on the emission frequency, which is less important now, but very importantly, it depends on the amount of light that actually enters the nanocrystal. It depends on the dielectric screening or the local field factor. And for quantum dots, this is much larger than for nanoplatelets, for instance. So just by changing the shape, you can enhance the emission of a nanoplatelet. Okay. Now, first I want to have a brief look at this oscillator strength, because if you want to determine the oscillator strength, the way you can do this is by first constructing the absorption coefficient again, the spectrum of the absorption coefficient. And then you can calculate the oscillator strength by the absorption coefficient times the volume of the nanoparticle, which is actually the absorption cross-section of the nanoparticle divided by the dielectric screening. So you can see this as a way to eliminate the role of the local field factor in the absorption properties. So the oscillator strength, therefore, is an intrinsic materials property. It just depends on the electron-hole overlap. Practically, you would do this by, if you plot the absorption cross-section of a material, by integration of the first half of the excitonic absorption, and then by doubling its value here, you would get the, say, integrated bandgap absorption coefficient. And from that, the integrated bandgap oscillator strength. Now we did this for nanoplatelets, and there we already saw one interesting aspect for these structures. Because when we then compare the bandgap absorption coefficient for many nanoplatelets of 4.5 monolayers, we see that they actually have a slightly smaller absorption coefficient than 3.5 monolayer nanoplatelets. The ratio is about 1.5. And like I said, after then correction for the volume, or in this case, the thickness of the platelets, we can calculate the oscillator strength. And from this ratio of about 1.5, you would see that you would have about 20% higher oscillator strength, 20% higher electron-hole overlap for these platelets. Now, the reason why this was quite a nice result is that it actually nicely correlated with other results that were published et al. In the Schaller group. Because you see that they made an independent measurement of the electron-hole overlap, or the excitonic radius. And in this case, you see that the exciton radius is about 20% smaller for 3.5 monolayer platelets, which nicely corresponds to the fact that the absorption strength, or the oscillator strength, is 20% stronger. So this was a nice confirmation in optical data of these, say, measurements that they did of the exciton radius. But I do want to also highlight something different. If you look at the area dependence here, the absorption strength is actually quite constant. Same for 3.5 monolayer platelets. And even if we look at the fluorescence decay, remember, because the absorption strength is correlated to the emission strength or the emission rate, indeed the emission rate of platelets doesn't change much when you change the area of the platelets. And this was a very interesting confirmation that at room temperature, the faster emission that we still get compared to quantum dots has nothing to do anymore with the so-called giant oscillator strength effect. I just want to say, pitch this term here today without going too deep into this, but it has to do with the notion that here the emission rate of a quantum well is actually expected to increase with the area of the platelet. So the bigger you make the nanoplatelet, the faster the emission rate, the stronger the absorption. But this only happens at low temperature for colloidal nanoplatelets. And it only happens at low temperature because at room temperature, there's lots of ways by which the exciton can scatter with phonons, so with defects and so on. So the area of the platelet no longer matters at room temperature. They all have more or less the same emission rate. And in fact, if I go back to the absorption coefficient, we then even trying to understand a little bit if they are even stronger absorbers than typical colloidal quantum dots. And what was quite surprising is that if you look at the absorption coefficient of quantum dots of catselenite and platelets of catselenite, they actually have more or less the same absorption properties. So platelets are very useful in many aspects, but you have to be careful when you look at the so-called giant oscillator strength and giant absorption strength and emission rate, because at room temperature, this does not strictly apply. And the enhanced absorption that you get in platelets is mainly an effect of shade-dependent dielectric screening. So it does mean that indeed, compared to quantum dots, the emission is still faster. And what was nice is now, because we have these two different sizes, we could also check Fermi's golden rule, which I showed you just before. As I mentioned, we calculated from absorption that the oscillator strength for 3.5 platelets compared to 4.5 platelets is 20% larger. But remember, Fermi's golden rule says that the emission rate is also depending on the frequency of the emission. And since blue platelets have a bluer band gap than green platelets, we can calculate that the emission should be 23% faster, simply because you shift the band gap. So if you put everything together, you see that you would even expect here, when comparing 4.5, the green ones, to 3.5, the blue ones, you would have 1.5 times faster decay times, which corresponds actually quite nicely with the 1.75 that we observe experimentally. So this is nice because then from this electrostatics, we can understand here the emission characteristics now and the absorption characteristics of our nanoplatelets. So now I want to shift gear a little bit, and for this part of the lecture, look a little bit at the concept of surface passivation and increasing the fluorescence efficiency and what happens when you grow a shell around colloidal nanoplatelets. So hopefully yesterday you already noticed that surface passivation is important, because when you have a bare nanocrystal, when you have a bare nanoplatelet, especially sulfur and selenium traps, the selenium traps would be here then, are very detrimental to the quantum efficiency of a material. They form so-called deep defect states slightly above your valence band and lead to non-radiative recombination of your excitons. In other words, a loss of fluorescence. So what you want to do is you want to push away these surface traps as far away as possible from your emitting cadmium selenide core. And you can do this by growing either a cadmium sulfide shell or growing a zinc sulfide shell. Just as a proof, here I have a very nice result from, I believe, the Demir group, which show that indeed, if you have a cadmium selenide nanoplatelet, and then through ALD, you coat it with sulfur, cadmium, and so on, each time when you grow an outer layer of sulfur, you have a very strong influence of these sulfur traps and a loss of fluorescence. So it's very important to control these surface traps if you want to get efficiently emitting core shell nanoplatelets. So probably many of you know that cadmium sulfide, if I go back one slide, cadmium sulfide is a very nice material to use as a shell on cadmium selenide. However, even though the electron, the hole stays confined to the core because of the large valence band offset, the conduction band offset is quite small. This means you can have electron delocalization here and a loss of quantum confinement for the electron. Now, to avoid this and really make sure that you keep a type 1, a so-called type 1 heterostructure, we aim to grow zinc sulfide around it. And you can see that the reason we do this is because you can increase the conduction band offset then again. So we devised a synthesis method to grow thick shells of zinc sulfide around the nanoplatelets. You can see it actually works. You have very bright green fluorescence, and the fluorescence stays very bright as you increase the zinc sulfide shell. The main reason we were able to do that is because when you work with these single source zinc sulfur precursors, in this case zinc diethyl dithiocarbamate, you can do the synthesis at slightly elevated temperatures. And these elevated temperatures help to grow a more uniform, compact zinc sulfide shell around cadmium selenide of a sizable thickness. Yeah. But I want to highlight here that at this point, contrary with what you would expect from colloidal quantum dots, the emission color also starts to change. So the core was emitting in the green, but the core shell started to shift until you got emission into the red for cadmium selenide coated with a very thick zinc sulfide shell. Now, the fluorescence didn't increase much. You see some effect of carrier trapping here at some point by an increase of this tail when the shell is very thick, but overall the initial decay didn't change much. So the fact that it didn't change much confirmed that we still had a type 1 heterostructure. It was not a type 2 or a quasi-type 2, but still the color changed. So what was happening? Well, for that, I need to go back to a little bit of theory again and discuss the light-matter interactions in semiconductors when you have absorption of light to create an exciton. Again, the general notion is that you solve the Schrödinger equation for this problem, but since you now look at the behavior of the general wave functions of electrons and holes, you have to also here take into account the electron-hole Coulomb interactions. So this Coulomb potential means the electrons and the holes attract each other, but very importantly, the Coulomb interaction is modified by the dielectric constant of the semiconductor. Again, I don't want to trouble you too much with the actual solving of this problem. Suffice it to say that if you want to solve this, again, you can separate this wave function into a in-plane part and a z direction part. You can then solve this problem for all these different directions separately for the electron and the hole. So the electron wave function in the z direction is described by this part of the Schrödinger equation. The hole in z direction has this part. And then we have here an in-plane motion of the exciton described by the center of mass of the exciton as it moves through the crystal. And then we have the relative motion of the electron around the hole, just like an electron interacts with a proton in a hydrogen atom. So this is essentially the two-dimensional equivalent of the Schrödinger equation for a hydrogen atom. So we know that this again gives you the, say, discrete energy levels for that system, where E mu is now the binding energy of the electron hole pair. Just like for the hydrogen atom, where you get 13.6 electron volt for the binding energy of the electron to the proton, here we can get solutions which give you the binding energy of the electron to the hole. And if you do this calculation, you would see that if you go from bulk to 2 dimensions, the simple fact that you have to solve this problem now in 2 dimensions, with alpha equal to 2 in this equation here, the binding energy of an exciton compared to bulk goes up by a factor of 4. But I want to also highlight a very important notion here. Remember that I said that if you here do the solution in bulk semiconductors, you have to take into account that the bulk semiconductor has a dielectric constant epsilon r. However, if you solve this problem now in 2 dimensions, you can see that the electron-hole Coulomb interactions no longer propagate through the crystal itself, like in 3D, but most of the field lines, they actually go outside the nanoplatelet into the low dielectric medium, like the organic solvent or the ligands. In this way, you can understand that the dielectric constant that you have to use here is not the one of the semiconductor anymore, but it's the low dielectric constant of the organic solvent that you have to use. If this number goes down, it scales with the square of the dielectric constant, the binding energy goes up dramatically. You can actually have 100 times stronger binding energy for excitons in colloidal nanoplatelets compared to bulk semiconductors. Okay, understanding this, we can actually have a look now at what happens with this band offset of, with the band gap of cadmium selenide when you grow a zinc sulfide shell. So first of all, I want to go back to what we discussed in the very beginning. Remember that when you have a nanoplatelet, the band gap is, say, calculatable by a particle in a box calculation, but you have to take into account the finite potential. Okay? When a quantum well like cat selenide is only surrounded by the organics, the band gap or the band offset with the organics is really high. The band gap of a typical organic medium is say 8 to 10 electron volt. However, zinc sulfide has a lower band gap with cadmium selenide compared to the organics. So the finite potential well just became a little bit smaller still when you start to grow zinc sulfide. So this means cadmium selenide zinc sulfide, again, because of the very strong confinement, still leads to some electron and hole delocalization. It's a type 1, but the electron hole wave functions slightly leak out into the shell still. And this reduces the quantum confinement. A reduction of quantum confinement means a redshift of, in this case, the fluorescence spectrum or the band gap of the semiconductor. So we can understand already part of the redshift when you grow zinc sulfide, because part of it is correlated with simple quantum confinement effects. But the second part, and this was then revealed by doing the K.P calculations for this cat selenide zinc sulfide heterostructure, the second part has to do with the electron hole Coulomb attraction. So I just explained to you that when you go from 3D to 2D, the exciton binding energy goes up dramatically because the electron hole Coulomb attractions mostly go through the organic medium. You can appreciate that when you go from a 2D back to a more 3D-like situation, because you grow another semiconductor now around your cadmium selenide core, you actually will reduce the binding energy again. So the reduction of the binding energy comes from the fact that in the center you have cat selenide, but part of the electron hole Coulomb interactions, part of the field lines now go through the zinc sulfide, which again is a high dielectric constant semiconductor. And it's in fact this behavior, this reduction of the exciton binding energy, which causes the most part of the redshift of the band gap after you grow a shell. And with K.P calculations, we can even quantify this. You see that by growing a thin shell of zinc sulfide, even one monolayer, you have some electron hole delocalization, reducing the quantum confinement effect, redshifting the fluorescence by about 50 nanometers. But then when you start to grow a thicker shell, the fact that you put more and more semiconductor material leads to a very strong additional Coulomb correction of the electron hole interactions, which means you have a further redshift of your band gap. These are calculations done without taking this electron hole Coulomb interaction into account, and you see that after 2 monolayers you have a constant shift. You don't shift the band gap anymore, but when you have here taken into account the Coulomb interactions, the fact that you grow a thicker and thicker zinc sulfide shell means you will further and further shift the band gap of this material. And this is a very nice way to, say, change green emitting cat selenide cores into red emitting zinc sulfide core shell nanoplatelets simply by playing with dielectric screening, with the optical constants of the material, with the electron hole Coulomb interactions, rather than quantum confinement effects. So for the second part, I would like to say emphasize that you can make core shell nanoplatelets as well. You can choose the material that you put around it, and when you put zinc sulfide, you can make a type 1 heterostructure with a very fast emission. Still, the color of the emission will change, and this is now, importantly, this has to do with Coulomb interactions rather than quantum confinement effects. Yeah. So this means that at the end of the line, we can now start thinking of making, for instance, very nice here, red, green, blue display applications, not just based on quantum dots, but now starting to be based on nanoplatelet systems or 2D systems, because you have here color tuning making green to red, but in addition, you have high absorption, fast emission, high quantum efficiency as well. So the general idea I want to bring to you in this lecture is that also 2-dimensional nanocrystals can be designed very efficiently to have varying emission colors. You can take precursors to tune the width. You can take the temperature to tune the thickness. You can play with the organic ligands. And very importantly, not just quantum confinement, but the notion that the dielectric environment plays a very important role here in the optical properties is something that you really have to remember. And during this lecture, I hope I could show you that not just the synthesis was important, but also the spectroscopic investigations and the K.P calculations, which then give us the insight needed into the band structure and the absorption fluorescence properties to go into various final applications like an LED, for instance, or a laser or whatnot. Now, I would like to ask the organizer if I have, say, the time, 5 more minutes to also go into energy applications. Okay.
Sure. Yeah, absolutely.
So I hope the audience is not saturated by the equations just yet. And I just want to say that this part is slightly lighter. But next to, say, light emitting applications, I just wanted to add a few more slides also on energy applications, because when you start to make heterostructures, you can actually do even more with, say, the interaction of light with, for instance, a 2D nanomaterial. I showed you that one important aspect of simple heterostructures is that you can take blue light and shift it down into red and green emission. This depends mostly on the Stokes shift that you can enable. And I don't want to go into this today, but there are particular applications, for instance, developed in the Bravelli group, where you can have these materials engineered for energy applications, such as luminescent solar concentrators. On the other hand, what I want to talk to you today about is how to make here a upconversion of 2 infrared photons into 1 visible photon, because this can also be leading to an enhancement of the efficiency of a silicon solar cell, for instance. But for this, we need more elaborate ternary heterostructures. Now, why do we want to also think about energy applications? That's because I think everybody is aware that climate change is real, and we should be somehow we should be concerned about this. So one way to be tackling this problem is to rely on renewable energy sources. And I think the silicon solar cell is a prime example of how you can use solar energy to, say, drive economy by converting solar energy into electricity. Now, despite the success, there's, say, a few particular problems with the silicon solar cell. If you think about it in terms of overall solar to electricity energy conversion. And one problem you have is that you have here a reduced efficiency of the solar cell in the blue. This also means that you can take one of these materials with a large Stokes shift, have absorption in the blue and re-emission into the red. This is not what I want to talk to you about today. Another problem is that there are also here infrared photons that lie below the band gap of the silicon solar cell. And of course, near and below the band gap of the silicon solar cell, the efficiency of the solar cell is also very low. But what we can try to do is have these infrared photons absorbed by a so-called upconversion layer, then being re-emitted back into the solar cell as visible light, which can then be absorbed and transformed into electricity. So how do we do this? For this, like I said, we need a little bit more elaborate structure because you need a combination of type 1 and type 2 band offsets. And with platelets, you can actually do this by, first of all, growing, for instance, a type 1 heterostructure with a layer of cadmium sulfide. Now, I want to highlight here that we only grow the cadmium sulfide around the edges of the platelet. So we only extend it in the lateral dimensions where there's no strong quantum confinement. And when you do that, you see there's no shift of the absorption or the fluorescence. The emission actually stays fast. So when you make a core crown, so-called core crown sulfide nanoplatelet, you actually make a type 1 heterostructure. On the other hand, you can also grow cadmium telluride around your nanoplatelets. When you grow cadmium telluride, you see a very strong shift of the fluorescence. Also, the lifetime becomes much longer, which means the electron holes are separated because the electron hole overlap is reduced. This is a prime, say, example or piece of evidence for a type 2 heterostructure. So on the one hand, we can make cadselenide cadsulfide with a type 1 band offset. On the other hand, we can make cadselenide cadtelluride with a type 2 band offset. So then we asked ourselves the question, what would now happen if we grow a ternary nanocrystal like that? Well, if you grow a ternary nanocrystal like that, first of all, you can do it actually quite easily. It's just a one-pot approach where you first grow cadsulfide and then subsequently directly inject some extra tellurium in the solution to grow this final cadtelluride layer. And if you look at the optical properties compared to the normal type 2 emission that you get from cadtelluride cadselenide, when you have this cadsulfide layer in between, we start to see additional emission peaks coming from direct gap recombination in the cadtelluride and the cadselenide. Now, I don't want to go into the reason why cadtelluride is emissive now, but the cadselenide is emissive because you have this barrier here for the holes. So what happens is that you can excite the system, you can photoexcite the system, you can have here electron hole recombination like this as the indirect transition giving rise to this red peak, but you can also trap the holes here into the cadselenide, giving rise to this small peak here. And this is now the prime example why you can have this system yielding 2 photon upconversion. Why is that? That's because for 2 photon upconversion, like I said, you need 2 infrared photons to be recombined into 1 green emissive photon. And with cadselenide, cadsulfide, cadtelluride, you can do this such. If you have absorption of a first infrared photon creating your indirect exciton, you can actually further shine infrared light on this material and have the hole do a so-called intraband transition. So you excite it deep into the bands, but since it's so deep now, the relaxation of the hole can go back to the cadtelluride, but there's also a finite chance it will relax into your cadselenide. So after double excitation of 2 infrared photons, there's a finite chance the hole ends up here. The electron was already in the cat selenide, and as a consequence, because the hole can no longer relax back to the cat telluride due to the barrier, you have here the possible emission of a green photon. And this is what we call fluorescence upconversion. That it works is actually demonstrated by this experiment here, where we took 2 red photons now, nearly infrared photons at 640, and indeed see emission of green light. It scales with the square of the input power, which indeed means that the green light is produced by 2 red photons. Now, I don't want to go too much into further detail. I just want to say, gave you this as an example that you can do more with nanocrystals and nanoplatelets if you start to engineer the band structure in more elaborate structures like that. Also, this is a, say, first example on 2-dimensional nanoplatelets. It doesn't mean that it's also the most efficient system, because we did a calculation here in collaboration with the Orum group. We did these measurements. You see that we need actually about 36 near-infrared photon pairs to have the equivalent of excitation to 1 visible photon. While the Orum group itself, actually, they have lead selenide-based systems where they only need 7 photon pairs. So this is still work in progress, but when you take 2D nanomaterials, you can even start to combine type 1 and type 2 nanomaterials by band structure engineering into these ternary heterostructures. You can even look for, say, additional fluorescence properties like fluorescence upconversion, which could be useful for energy applications. Okay, so with this, I would like to end my talk, give you the general conclusions that we can make nanoplatelets of various shape and size, yielding all these nice colors from blue to red now. By doing this, by growing a zinc sulfide shell, we can make them good for LED applications, because we can take blue light, absorb it, and make red to green. By making these ternary structures, we could even do upconversion. So I hope you enjoyed the lecture of this morning, and I would just like to end by saying, I think you heard me already saying that we collaborated with lots of people. These are the people from the Physics and Chemistry Nanostructure group at Ghent University, but I also had some excellent former team members. We had people at the Weizmann Institute here doing the upconversion with us. The people in the University of Zhejiang are really excellent people to do these K.P calculations. With the Brovelli group, we do the part of the spectroscopy, and also part of the work was done when I was still at IIT in Genova, and we are still collaborating for structural characterization of these nanomaterials.